Okay, thank you for the introduction, thank you for lunch, and also thank you for the opportunity to discuss exotic B series and S series. So in this presentation I will discuss how the formalism of rooted trees can be used in the stochastic context. And also we will also discuss ergodic integrators and the order conditions with respect to invariant measure. So let us start with a small, it doesn't work. I can just click. Oh yeah, now it works. So a small preview. We will work with the overdamped Langevin equation, where F is a potential, is a gradient of a potential. W is a standard Wiener process, and the noise is additive. So we will study the integrators applied to this equation, and while in the course of this study we encounter grafted forests. So we encounter grafted forests of the following form and exotic forests. So the grafted forests are bicolored forests with the two colors of vertices. We have black vertices and grafted vertices, which are denoted by these crosses. And the grafted vertices cannot have incoming edges, so they can only be leaves. We also have exotic forests. So here are some examples. So we see that the exotic forests are grafted forests in which all the grafted vertices are paired. And the pairing is denoted by these numbers. So here we see that these two are paired and these two are paired. So when two numbers are the same, this means that the grafted forests are paired. And this kind of forests are used to represent differential operators. And here you see some examples. So here on the left we have a differential operator corresponding to the grafted forest. And on the right we have a differential operator corresponding to the exotic forest. And we can see that the differential operator corresponding to the grafted forest is a random variable due to this xi, which is a Gaussian. So now let us start with the preliminaries. Let us start with the deterministic case. So we have dy dt equals fy, where f is a smooth vector field. Then we can integrate this problem using Runge-Kutta methods. So they have the following form. And the coefficient of the Runge-Kutta methods can be listed in a Boucher tableau here. Then we can take the f of capital Yi and we can Taylor expand it around y0. So when we do that, we are able to write y1 as an infinite sum, where every term with the sum is a vector field applied to y0. So here we have identity, here we have f prime f, and so on. And the coefficients of the terms are given by the Runge-Kutta coefficients. So we do that because we can also do that with the exact solution. We can take y of h and Taylor expand it around 0, and then we get a similar infinite sum. And then when we compare the coefficients, we get the order conditions for Runge-Kutta methods. So we can apply this reasoning and generalize it further. So we can take the set of rooted trees, so some rooted trees are listed here, and we consider functionals A from T to R. Then B series are formal sums which are characterized by such functionals, which are formal sums of vector fields. So here we see the identity, HF, A square, F prime F, and so on. And the coefficients are given by the values of A. So here we see A applied to the rooted tree, which corresponds to the vector field in question. So here we use the correspondence between vector fields and rooted trees. So here, for example, we have HF, which corresponds to a single vertex tree. Here we have F double prime FF, which corresponds to this V-shaped tree, and so on. So as I have mentioned before, exact solution and Runge-Kutta methods are B series, which means that we can write order conditions for general B series. So here we see the order conditions for order 3, and here we see that the Runge-Kutta coefficients. So this is the function corresponding to the Runge-Kutta method, and here the constants come from the Taylor expansion of the exact solution. So this theory was originated by John Boucher in the 60s, and then developed by Ernst Heirer and Gerhard Wenner in the 70s. And another nice property of this structure of B series is their relationship to the Hopf algebras. For example, if we consider B series and their compositions, then there is a nice relationship with the Konzen-Kreimer-Hopf algebra, which was introduced in '98 to handle divergent integrals in quantum field theory. But in this talk, we'll mostly focus on S-series. So if B-series are based on rooted trees, then S-series are based on forests. And if B-series are formal sums of vector fields, then S-series are formal sums of differential operators. So here we see a set of forests with some examples in it, and symmetry coefficient sigma with some values. Then originally, S-series were introduced to study first integrals. But in our case, we're going to use them a bit differently. So given a map phi from Rd to R, we can compose phi with a B-series B of A. Then this can be written as a differential operator S of A applied to phi. And this differential operator can be written as a formal sum over forests, where every term in this sum is a differential operator corresponding to a particular forest. And the coefficient is given by the extension of the map A from trees to forests. And then we divide this coefficient by sigma of P, by the symmetry of the forest. So since we work with B-series in a stochastic context, we're interested in studying the expectation of phi of B of A. So here we have phi composed of B of A, which means that we have to study, we can consider it as an S-series applied to phi. Okay, so now let us talk a bit about ergodicity. So a problem is ergodic if the trajectories of its solution are characterized by a certain invariant measure. So this is the characterization here expressed by in this formula. So what we see here on the left, we see an average of the trajectory, and on the right we see the integral with respect to the invariant measure mu. So since we work with overdamped Langevin equation, we have that d mu is equal to z, which is a normalization coefficient, e to the power minus vx, where v is the potential of the problem. And since we work in a stochastic context, we have multiple ways to converge. We can converge in a strong way, where we are interested in particular trajectories. We can converge in a weak way, or we can converge in invariant measure if we work with ergodic problems. And this gives us several kinds of orders for numerical methods. So we can have a weak order defined here, and an order with respect to invariant measure, which has the following form. So order with respect to invariant measure basically tells us how well does our numerical integrator approximates the invariant measure of the original problem. So here we have the average of the trajectory of the integrator. And a nice property is the following. So the order with respect to invariant measure is higher or equal to the weak order. So this is discussed in Talay Tubaru in their paper. But if we are only interested in the invariant measure, then we have a bit more freedom. For example, if we consider the stochastic Runge-Kutta methods of order 3, then there are 15 weak order conditions and only 9 order conditions with respect to invariant measure. So this finishes the preliminary section, and now the main part of the presentation starts. So the presentation will be split into 2 parts. In the first part, we're going to consider exotic S-series and study their algebraic structure a bit. And in the second part, we're going to consider order conditions with respect to invariant measure. We're going to discuss a theoretical algorithm which generates this kind of order conditions. And we also study these order conditions and show that a lot of them can be satisfied automatically. So let us start with the first part. So let us start with the exotic S-series. We recall that we work with the overdamped Langevin equation of the following form. We also work with grafted forests and with exotic forests. So exotic forests are grafted forests in which grafted vertices are paired. So let us define S-series of a grafted forest and exotic S-series. So here we see the 2 definitions. So on the left we have an S-series defined over grafted forest, and on the right we have exotic S-series, which are S-series defined over exotic forests. And we can see that the two formulas, so they're very similar, and they're also very similar to the classical definition of the S-series. Here the main difference is the fact that here we take the sum over a grafted forest, here we take the sum over exotic forest, and we also define the symmetry and the map F over the appropriate sets. A nice property of this kind of, so there is a kind of relationship between these two S-series. So since the differential operator corresponding to a grafted forest is a random variable, we can take an expectation of it. So when we take an expectation of a series of a grafted forest corresponding to the functional A, then this is equal to an exotic S-series corresponding to a natural extension of the functional A from grafted to exotic forest. And this is a bit surprising because this fact is due to the fact that here we have these sigmas in the definitions. So these sigmas, they make this nice relationship happen. And it's surprising because originally this sigma is introduced to simplify the description of the composition law. And we're going to discuss composition next. So let A and B be two functionals over exotic forests. And let delta CK be the constant Kramer coproduct defined over exotic forests, where this coproduct, what it does, it takes an exotic forest and then divides it in two parts in all possible ways, right? So it's a notion dual to the notion of a product. Then if we compose the exotic S-series of A and B, then this is equal to the exotic S-series of a convolution of A and B, where the convolution is taken with respect to the constant Kramer coproduct. And here we have an example. So here we have A convoluted with B of a certain exotic tree. Then we have a sum over all ways to split this tree in two parts, in the left part and the right part. Then we apply A to the left part, B to the right part, and we multiply the results. And we get a functional. So to prove this, this statement, what we do? Yes?
I'm sorry, I just have a question here regarding the last slide.
Yes?
Maybe I missed it. So you have A defined over your grafted forests.
Yes, here.
And then you say, and then you take expectation, and now you get something over the exotic forest.
Yes, so this A, okay, I use the same letter, but it's not exactly the same thing. So here, this A ignores the pairing, and when you ignore the pairing, you get a grafted forest, and then.
Okay, yeah. I have a question. I don't know if this is the right place to ask it, but these exotic series, this looks for me very much like a Feynman diagram. And if I have an SVDE and I have like the tree, or the forest, which is representing the stochastic process, and I take an expectation, I wick pair exactly like you do, and then if I just do a little bit of node counting depending on the state of the potential from the problem, I recover the Feynman diagrams by the physicists. And you can put, there's also like Dominique has some papers on half algebra structure of Feynman diagrams. Is this what you're seeing here, essentially some morphism between the con-Kramer trees and the Feynman diagrams?
Yeah, it's related. But in your formula for the coproduct, you notice that you are not allowed to cut the Laiana. That means you cannot have one figure 1 on the left and the other figure 1 on the right of the tensor product.
Yeah.
Am I right?
Yes, yeah, that's true. Yeah, I didn't really look at it from Feynman diagram point of view, yeah, but it would be interesting to discuss.
It's essentially just another way of writing the same ideas.
Yeah. It would be interesting to discuss. Yeah. So to prove this statement, so I repeat, the statement is that when we compose two exotic S series of corresponding to A and B, then we get an exotic S series corresponding to the convolution product. So okay, what we can say it means is that we have a map ES, which sends the convolution product to the product which is the composition of differential operators. So here we can look at ES as a map, which is a composition of three simpler maps. So here we have F, a sigma minus 1, and delta minus 1. So delta minus 1 takes a functional over exotic forests and returns a formal sum over exotic forests, where the coefficients are given by the functional A. And then A sigma minus 1, it takes an exotic forest and divides it by its symmetry. And then in the end, F takes an exotic forest and returns a differential operator corresponding to it. So that's how we can write ES. Then what we do next is we look at the Grossman-Larsen product. So here we define a Grossman-Larsen product on exotic forests. We denote it by a diamond. And we use the fact that F is injective, so we can define the Grossman-Larsen product over exotic forest to have, by requiring this property that F sends the Grossman-Larsen product to the composition of differential operators. Originally, a Grossman-Larsen product is defined in a combinatorial way, but here we can do this way just for presentation purposes. Now, so we have to analyze how the convolution product here changes as it passes through the map ES. So delta minus 1 sends the convolution product to the product which is dual to the Konzen-Kramer coproduct. So this comes from the definition of the convolution product in the delta minus 1. Then sigma minus 1 takes the product dual to the Konzen-Kramer coproduct and sends it to the Grossman-Larsen product. And then the Grossman-Larsen product, in this case, this is by definition, but it's a property of the Grossman-Larsen product, or of F. So Grossman-Larsen product gets sent to the product, which is the composition of differential operators. And this finishes the proof of the statement. Now, this delta minus 1 and F property are straightforward, but the A sigma minus 1 here requires some work because the original proof of this fact on classical trees, it required the trees to have one root. In our case, for exotic trees, an exotic tree can have multiple roots, and here we have some examples. So here we have an exotic tree with 2 roots, an exotic tree with 3 roots, and these are trees because we cannot split them further into subtrees without cutting some edges or breaking some pairings. Right, so we found an alternative approach of proving this fact that also works in our case. And this finishes the first part. In the second part, we're going to discuss order conditions for invariant measure sampling. And here we have a list of some order conditions. And we note that every order condition corresponds to a certain exotic forest of a nice shape. So here we have 4 of them. And an order condition is satisfied if it's equal to 0. Now we will also look at a property which says that for example, in this case, the second order condition is satisfied automatically if the first order condition is satisfied. Right? So this allows us to reduce the number of order conditions significantly. So we present a theoretical algorithm that generates order conditions. So the algorithm generates these omegas of pi, and we obtain an order condition if we say that it should be equal to 0, where pi is from a nice subset of exotic forests. Now we have the following property. Let this square cap sigma denote the renormalized concatenation product. And then if we consider stochastic Runge-Kutta methods, then we have a nice property of this omega map. So omega of the pi1 concatenated with pi2 is equal to the omega of pi1 times omega of pi2. So what it means is the following. So if the order condition corresponding to pi1 here, or pi2, is satisfied, this means that this omega of pi1 is equal to 0, which means that the omega of the concatenation of pi1 and pi2 is equal to 0, and the corresponding order condition is satisfied. And here we have some particular examples of this property. So we have a small exotic forest with some, and this is equal to 1/2 omega of one tree times omega of the other tree. And this 1/2 comes from the fact that we consider a renormalized concatenation product. And here are the expressions of these omegas for the particular forests. Okay. So to actually prove this property, we have to analyze the action of the algorithm. So the algorithm acts in a linear way. Okay, acts in a linear way. So we can restrict our attention to exotic forests, to how it acts on exotic forests. And here we have an example. So here we take an exotic forest with this shape. Now, what the algorithm does to it is it sees this pair of grafted vertices and it moves it down the tree. Now we have a tree which has two roots, and one of them is a grafted vertex. And then what it does, it takes this grafted vertex and it connects it, grafted root, and it connects it to all the other vertices. So that's how we get these three first terms. And then in the last term, what it does, it replaces the pair of grafted vertices by a black vertex and multiplies it by 2. And here, these are all, it changes the sign, so this is a negative sign. So this gives some idea on how the algorithm works, but it doesn't really allow us to analyze its properties, because, at least combinatorically, because here we have a linear combination. So we split this transformation into 4 transformations, transformation chains, and we call them labeled transformation chains, or LTCs. And here we see that every term in this transformation chain is a tree or an exotic forest. And then we can analyze it combinatorically. And here we ignore the coefficients. So here we have -1, -1, -1, -2. We ignore them, we treat them separately. Okay, so these LTCs are the main tool that we use. So what we can do is we can take an LTC of an exotic forest and we can split it into several LTCs. We can also take several LTCs which are compatible and combine them together. That's the first ingredient in the proof. The second ingredient is the fact that the algorithm defines a linear map, so it's a mathematical object which can be studied. And then the third ingredient is the fact that if we consider stochastic Runge-Kutta methods, then they are B series over grafted forests, and they form exotic S series ES of A, with A respecting the concatenation product. And that's a nice property, but it's a general property for all exotic S series which come from B series. And this is also true in the classical case, in the deterministic environment. So these 3 ingredients allow us to prove this property of the omega, which we want to prove. And then we can use it to say that these 3 order conditions we see here, they can be ignored. They are automatically satisfied if smaller order conditions are satisfied. So this allows us to decrease the number of order 3 conditions for invariant measure sampling from 13 to 9. And originally this property was found through manual computation in the paper by Adrien Laurent and Gilles Villemin in 2019. And here we generalize this property and prove it for a general order in general forests. So this basically means that we can ignore all the order conditions corresponding to exotic forests, and we should only consider exotic trees. So to conclude, so in this talk we defined exotic S series. We have seen a nice relationship between exotic S series and the grafted and S series of grafted forests. We also introduced a theoretical algorithm which generates order conditions with respect to invariant measure, and discussed its multiplicative property. And ongoing work includes description of the substitution law for exotic S series, and a development of a symbolic package for manipulation of forest-like graphs, which is done in collaboration with with Jean-Luc Policon from Computer Science Department of University of Geneva. So thank you for your attention.